All right, next we're going to study the idea of Venn diagrams and set operations. Um, Basically, we're going to take a look at how sets interact with each other. Interact might be a weird word, but how they overlap, or different ways of looking at how they're similar to each other, maybe. And so here I have three sets. I have D is the set of all digits, all 10 digits, 0 through 9. E is the set of even digits, 0 through 8, the evens. And T is all the digits that are divisible by 3, right? 0, 3, 6, 9. And what I want to do is look at some of these sets out, and how the elements, how do I say this? I want to look at how the elements fall into these three different sets. Okay, so kind of the elements in particular now. So if you'll notice, the element 0 happens to fall in all three of them. Okay, there's another point that falls in all three of them, or another element, that's the element 6. 6 falls in all three of them as well, so 0 and 6. There are all of the elements of E fall into D, and all of the elements of T fall into D. So that gives us some subset ideas, right? So we know that, go back to what we were talking about, 0, 0 is an element of D, E, and F, or F, T, just going alphabetical there, D, E, and T. We would say that E is a subset of D, and T is a subset of D. Okay. Now, is E a subset of T? No, because there are elements like the element 2, which are in E but not in T. Similarly, T is not a subset of E, because there are elements, 3 for instance, that is not in E. It's in T but not in E. So they're not subsets of each other, right? So E is not a subset of T, and T is not a subset of E, right? Okay, so that gives us some subset idea. So what are the elements that are in both E and T? We said 0 and 6, right? So 0 is an element of E, 0 is an element of T, 0 is an element, I'm sorry, not 0, 6 is also an element of E, and 6 is also an element of T. So you have 0 and 6 are elements of both. Okay, so there are some interesting ways to visualize sets. We call them Venn diagrams. It's a way of just kind of picturing it with a geometrical representation. In this case, we have three sets. We have one set that's kind of the universal set. It kind of oversees all the other ones. It contains all the points of the other ones. Okay. In that kind of set, we call it the universe, actually. And we usually use a big box, it could be a square, rectangle, to represent all the points that are in D. Okay, so D, in this case, is our universe. The universe is basically the largest set. It's like a superset. It contains all of the other sets that we're discussing at the time, right? So D is that set, the set of all digits. And in this set are all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, right? They're all in there. And I just scramble them up. It's kind of like having a bag full of numbers, right? They're all in there. Oh, and 0. I didn't go 0 in there. Hi. Okay, so they're all in there. Now, we don't usually list them all out. We don't have to list them all off. We could. What I'm going to do then is represent E and T also in this universe. And so E and T are just going to be circles. They're kind of like blobs right in the middle somewhere. Not directly in the middle, but in there, in the interior. And they contain some of those points. So what we tend to do is use circles. That one is E. And now E is going to contain, this circle should contain all of the points 0, 2, 4, 6, 8. T is going to be another circle, and it's going to contain 0, 3, 6, 9. Well, interestingly, I want 0 and 6, because it's in both, to be in both circles. So how do I make another circle that'll have points in both of them? Well, I just have to overlap them a bit. Okay, so T is over there. Okay, so now we have the universe set D, which are the digits, and then set E, the evens, and set T, which are the triples, right, the multiples of 3. And so in these sets, in these regions, I can name or list all of the elements. All right, so in, let's say, set, or the points, the elements that are in both E and T are going to be in this overlapped region here, 0 and 6. So I could just write those in, 0 and 6. They're going to be in that overlap region. The rest of set E, this is going to contain the other points, 2, 4, and 8. Okay, they're all going to be in there. They're in E, but not in T. T is going to contain, the other region of T is going to contain, let's see, 3 and 9, because those are the digits that are not in the overlap, but they're still in T. And all of the digits that don't occur in either of those, but are still digits, are going to be in the outside, kind of in this, exterior space here. Still within D, but outside of E and T. Those numbers are going to be 1, let's see, 0, 2, 3, 4, 5 is not in either of those. 6, 7, 8, 9. So 1, 5, and 7. Okay? Those are the only 3 digits that are neither divisible by 2 or by 3. Okay? Okay. So that should give you an idea of how we would construct a Venn diagram. Okay, Venn diagram is this visual image. It shows the elements of the set. It shows kind of the relationship between the sets. Also, what's interesting is that anytime a set is a subset of another, it will be completely contained within it. Okay, so set E is a subset of D, so its shape, its circle, is completely inside of that. It could be the case that maybe I had picked another set, maybe I picked set Z or something, and it includes just the point 2, or just the element 2, in which case I would have the circle right here. It would be completely contained within E, and so that you have, if anything is a subset of another set, its geometrical image is completely contained inside the larger set. So now, just to summarize a couple things and show you some variety here, not every Venn diagram has exactly this relationship in the sets. Here I've got some overlap, but there's some other possibilities. You could have the case where 2 sets are disjoint. We say they're disjoint. Basically means there are no common elements. And in that case, you would have a Venn diagram where the 2 shapes don't overlap. Okay, so you might have something like this, where you have set A, set B, and the universe, and they're not overlapping. Okay, that would be disjoint sets. You could also have a set that's a subset. I mentioned this just a moment ago. Get rid of some of this. So you could have subsets where, say, A is a subset of B, in which case A might be a larger set, and B might be the larger set, A might be inside of it. So here's our universe. B is the superset, A is the subset. Alright, so that's a possibility as well for a Venn diagram. You could also have the case where you have equal sets, where the two sets are exactly identical. Alright, and so you have A is equal to B, in which case your Venn diagram just has a single circle with both A and B labeled on it. Okay, so that's a possibility, and of course the one that we just saw, where there is an overlap, but then there's some things that are not in that overlap as well.